Okay, so this is section 10.3. There are really two topics that we're going to address in this section. One is how to represent graphs in various ways, and the other is a subject called graph isomorphism that we're going to get to in a slightly later video. So I want to say a couple things about representing graphs to begin with. Uh, so far, we've been representing graphs almost exclusively with diagrams like the one on the left over here. That's a great way to represent a graph if you're just trying to understand what it is and if you want to be able to visualize it. But it's not a great way to represent it if you want to do anything with that graph using a computer. So if you want a computer to store that graph, right, then you need to represent it in a way that a computer can understand. Computers aren't good with diagrams. They are good with lists, and they can do lists of lists to make arrays. So we are going to look at two ways to represent a graph using using a table and a matrix. These are representations which, when stored by a computer, you could iterate through that list or array in such a way that you would be able to then perform like algorithms on that graph in order to identify things like whether or not it's bipartite, discussed in the previous video, or like what the shortest path between two given vertices is, which is something that we'll be looking at. Well, actually, no, we won't be looking at it together, but one of the teams will be looking at that for their project and presenting on it at the end of this semester. So, all right, let's begin. That was a bit of a long introduction. All right, so first off, if I want to make a table, if I want to make a table to represent this graph, really, the way to do this is to have two columns, one for the vertices and one for the adjacent vertices. So this is we're going to represent all of the different adjacencies in the graph. So we're going to have a row for each vertex, A through E, in this example. And then we'll say, all right, for vertex A, what is it adjacent to? In this graph, it's B, C, and E. And that's it. We just make that list and enter that list in this second column. What is vertex B adjacent to? Well, in this case, it's just A. C is adjacent to A, D, and E, and so on. We'd put C and E here, and then A, C, and D here. So there we go. So this table contains all of the same information that the diagram did. If I gave you this table, you would be able to reproduce that diagram, and vice versa. In other words, the table is the entire graph. Okay. All right, so that's one way to do it. Another way to do it is with a matrix. Now, the matrices that represent graphs are kind of similar to matrices that represent relations. And one of the ways in which they're similar is that you need to identify the elements of the set with the rows and columns of the matrix. So in this case, the set is the set of vertices. So we need to put those vertices in some specified order. Since they're letters in this case, it's obviously I can put them in the alphabetical order, so that's nice. But if it was other objects like people, you would just arrange them in whatever order suits you. So I'm going to use a red pen here to label the rows of my matrix. And then whatever ordering I use for the rows, I have to also use that ordering for the columns. And the reason it has to be the same is so that the entries on the main diagonal correspond to a vertex being adjacent to itself via a loop. We want that in order to be able to look at our graph and quickly get some information from it. So now that I've done that, now I'm going to build the graph or build the matrix itself with putting the entries in. And I'm going to put a 0 when vertices are not adjacent, and I'm going to put a 1 when they are adjacent. Since this is a simple graph, there's only ever up to one edge connecting any two vertices. Now, I'm going to go do this one row at a time. For row A, it's not adjacent to itself because there's no loop, but A is adjacent to B and C and E, not D. So that's my row for A. For B, it's adjacent to A, but none of the others. All right, I'm going to pause the video if I. Okay, there we go. So there's the full matrix that represents that graph. Okay, and I want to point out a couple things about that matrix. First of all, since our graph in question here is simple, there's a few things we can say about this. One is that we only have, oops daisy, sorry. We only have zeros and ones. In a simple graph, vertices are either adjacent or they're not. That's it. And the other thing about this is we have only zeros on the main diagonal. Okay, and that's because we don't have any loops. The other thing I want to point out about this graph, it has to do with the fact that it is undirected. The fact that this graph is undirected means that whenever A is adjacent to B, B is also adjacent to A, and in general for any two vertices. So this matrix has symmetry over the main diagonal. All right. So there's an introduction to representing matrices. I'm going to stop the video and then make another one with a couple other examples before we move on to graph isomorphism.